Welcome to This Explainer. Today, we're stepping right into the shoes of a lead engineer. I'm going to be your mentor as we master magnetic particle testing, or MT. This is one of those incredible, quiet success stories in modern engineering. It's a brilliant, non-destructive testing method that literally prevents catastrophic failures in the planes we fly and the pipelines fueling our cities. And the wild part? It relies entirely on the invisible laws of magnetism to expose hidden dangers.
Okay, let's dive right in by anchoring ourselves to the rule of three. If you take away anything from our session today, let it be this step-by-step guide. These are the three vital, non-negotiable actions you've got to take to test any component out in the field. First, you induce magnetization. Second, you apply your detection media and hunt for flaws. And third, a step you can never ever forget, you demagnetize the part safely. Master these three, and you've mastered the craft. To make sure you're fully equipped for the field, here's our playbook for today. We'll start with 1, understanding the magnetic foundation. Then we'll move through 2, step 1, induce magnetization. 3, step 2, apply and detect. And 4, step 3, demagnetize safely. Finally, we'll wrap up with 5 tools for real-world success. All right, section 1, understanding the magnetic foundation. Before we flip a single switch or pick up any gear, we really need to understand the invisible forces at play here. Frame these fundamental physics concepts not just as theory, but as your primary tools. Because honestly, if you don't understand the metal, you can't test the metal. It basically boils down to 2 competing properties within ferromagnetic metals: permeability and reluctance. Think of permeability just like electrical conductivity. It's how easily the magnetic flux lines flow through the material. Reluctance, though, that is exactly like electrical resistance. It's the metal fighting back, resisting the alignment of its internal magnetic domains. Your job as an inspector is to understand how your specific metal balances these 2 forces. Take a look at this virgin curve charting upwards. When an unmagnetized piece of metal first experiences a magnetizing force, we map its response. That steep, upward initial line indicates high permeability. It means the microscopic magnetic domains inside the metal are easily snapping right into alignment, north poles pointing one way, south poles the other, as soon as that force hits. But watch what happens when we apply a negative force. See, once a metal is magnetized, it really likes to hold onto that magnetic field. We call that property retentivity. To break that grip and safely reduce the net flux density back to 0, we have to apply an opposing force, known as coercive force. We are actively pushing those aligned domains back out of order. And that brings us to the whole shebang, this beautifully complete S-shaped hysteresis loop, which perfectly illustrates the metal's unique magnetic memory. By continuously reversing and increasing that magnetizing force back and forth, we form this loop. It tells us everything. A steep loop means high permeability. A shallow one means high reluctance. Understanding this cycle is the absolute key to finding flaws and eventually making the metal safe again. To ground all this heavy theory, remember the massive real-world success story that kicked this all off. Back in the late 1800s, inspectors noticed that a simple compass needle would mysteriously deflect when passed over a magnetized military cannon barrel. Why? Well, that deflection was caused by a hidden crack. That one simple, life-saving observation paved the way for the sophisticated engineering techniques we rely on today. Okay, section 2, step 1, induce magnetization. With our foundation firmly set, we're ready for our first major action in the field, actively creating a magnetic flux field right inside our test object. When you're out there maybe wrapping a heavy cable around a pipe, you need to know exactly where your magnetic field is going. So use this classic mentor's trick, the left-hand rule. Just point your left thumb in the direction of the electron current flow, from negative to positive, and your fingers will naturally wrap around the conductor in the exact direction of the magnetic field lines. It's a foolproof physical check you can do anywhere, anytime. Next up, you've got to decide how to power that field, and choosing your electrical current wisely is absolutely crucial, because they do very different things. Direct current, or DC, pushes deep into the metal, making it your go-to tool for finding hidden subsurface manufacturing flaws. Alternating current, or AC, on the other hand, constantly reverses. This creates a skin effect, keeping the magnetic field tightly vibrating right near the surface. So, AC is your absolute best bet for rapidly hunting down fine, in-surface fatigue cracks right on the exterior of a part. Moving right along to section 3, step 2, apply and detect. The metal is primed, the field is active. Now we reach the climax of the process, where we force those invisible flaws into the light.
Remember our chat about reluctance? Well, whenever a crack interrupts those flowing magnetic flux lines inside the metal, the reluctance heavily spikes. The magnetic field always wants the path of least resistance. So, with the crack blocking it, the field is literally forced to break out or leak into the air just above the surface of the metal, forming miniature north and south poles right at the defect. And here is the big payoff. This is where the magic happens. We apply our detection media, these finely milled ferromagnetic particles. Because they're highly permeable, they're instantly and powerfully attracted to that magnetic leakage field. They literally pile up, bridging the gap of the crack, and create a highly visible, jagged line exactly where the flaw is. You've just taken a completely invisible threat and made it undeniably visible. As an inspector, you're going to choose your particles based on your environment. Working on a rough weld out in the elements, you'll probably grab dry-colored powders, reds, grays, or yellows, to contrast with the metal. But if you're in a highly controlled environment inspecting, say, critical aerospace parts, you're using a wet suspension of fluorescent particles. View those under an ultraviolet black light in a darkened room, and even a microscopic hairline crack is going to glow brilliantly. Which brings us to Section 4, Step 3. Demagnetize safely. You found the flaw, or maybe you verified the part is safe. But listen to me carefully here. Your job is not done. You haven't successfully finished until you return that component to its normal, unmagnetized state. This step is 100% non-negotiable. You might be wondering, why is this so absolutely critical? Well, because residual magnetism has severe real-world consequences. Skip this, and a highly magnetized aircraft or ship component could critically throw off navigational compasses. Or, if a welder comes in after you to repair the crack you just found, your residual magnetic field will violently deflect their welding arc, a dangerous phenomenon known as arc blow. And trust me, you do not want an angry welder chasing you off the job site. To completely erase the metal's magnetic memory, you just need to strictly follow 2 simultaneous steps: successively reverse the polarity and gradually decrease the field strength. We usually pull this off simply by passing the part through an alternating current field and slowly pulling it away. AC's natural reversing waveform does all the heavy lifting for you, stepping that hysteresis loop down until the residual flux is basically 0. All right, final stretch. Section 5, Tools for Real-World Success. We've covered the physics and the process. Now let's step off the chalkboard for a second and talk about the actual hardware you'll be getting your hands dirty with to save lives and protect infrastructure. You've basically got 2 main categories of tools. First, you have massive stationary units, often called wet horizontal units. These big guys are built for high-volume factory lines, where you clamp parts, like drive shafts, right into the machine to magnetize them. Then, you've got mobile units. This is your rugged, go-to companion for the field. You can roll it right onto a site, run heavy cables to a large structure, and use localized prods or yokes to inspect sections of a bridge or a massive pipeline exactly where it sits. By mastering these principles, you're stepping into a vital role that keeps our entire modern world functioning. So, as you leave this explainer and look at the engineered world around you, the cars, the buildings, the aircraft, I want you to ask yourself, what other invisible forces and hidden tests are quietly working in the background to keep us all safe right now? Keep questioning, keep learning, and I'll catch you in the next explainer.